Let's take a look at these two graphs. The graph on the left has the number of dogs earned across the x-axis, and it has frequency going up the y-axis. This is a bar chart. It's for discrete data and it has gaps in between each of the bars, and we use this only for discrete data because it has certain values it produces, so number of dogs, it will fit into one of those categories. Whereas the graph on the right here, this is a histogram and the y-axis will be the frequency density. And we use these for continuous data, so we've got weight going across the x-axis and there are no gaps on this at all. And so this is why this graph is used. Now we can take a look at the shape of these curves. The graph on the left has what we call a positive skew, so it's skewed over to the left hand side. And if we take a look at the graph on the right here, we have a negative skew where the graph is more spread out towards the right hand side of that data. So let's take a look at working with histograms. So how many people had a dog that weighed more than 50 kilograms? So the first thing that we need to do is look at the formula. So the frequency is equal to frequency density multiplied by the class width. Now we have our frequency density going up the y-axis here, so that will be the height of the bar, and then we also need the width of the bar as well. So we're interested in this one. It goes up to 2.5, that's the frequency density, and it has a width of 10, so that's the difference between 50 and 60, and therefore the frequency of this bar is 25. So this is important when you're looking at histograms. The area of the rectangle represents the frequency. Now you can also get asked questions in reverse. So if you knew that this bar represented 25, then you could work this out in reverse in order to work out what the frequency density would have been. So if you wanted your frequency density, that would be your frequency divided by your class width. And so if we knew the bar was up to 25 and we knew that the class width was 10, then that would tell you that the frequency density was 2.5, and this is often something that comes up in questions. So just get rid of the writing on here. Now, given that 100 people were recorded in the survey, what is the probability that a person that had a dog weighing less than 35 kilograms is selected? So this represents 100 people, which makes it a little bit easier when we're working out that probability. The first thing for us to do is work out how many weighed less than 35. So this is where we need to work out the area of each of those bars, and we're only working out half of the bar between 30 and 40. So that gives us our 9, so that's 27 in total. So the probability there is 27 over 100, which we can write as 0.27. Have a go at exercise 2.2 on page 144. So we're going to take a look at the mean, median and mode for this list of data. So this is discrete data. Now the mean, here's the formula. We say x bar is equal to the sum of x over n. So this symbol here is what we use for the summation of something, the sum, and it's the Greek letter sigma. That just means that we've added up all of that data and we've divided by the number of pieces of data that there are. So if we add up all of those pieces of data in the box, that comes to 203 divided by 10. So x bar, the mean, is equal to 20.3. For the median, we need to put the data in order first, and then we need to identify the middle of this data, and we can do that in a couple of different ways. We can either cross off from either end until we get to the middle. Now, The middle in this case is between 20 and 21, so we take the midpoint, which is 20.5. An alternative way of doing this, as there are 10 pieces of data, we have n equal to 10. The median can be found at n plus 1 divided by 2. So that would be 5.5 when n is equal to 10, and that means that the position of the median is in the 5.5 piece of data. So if that's the first, the second, third, fourth, that's the fifth piece of data, that's the sixth, and we can see that this then would be the 5.5 piece of data. Now the mode is the easiest to calculate. This is the most common, and in this case it would be 19 and 21, so we say this is bimodal. So let's take a look at different sets of data, and here we have a table of data for us to work out the average. So taking a look at this table of data and working out the mean, the median and the mode. For the mean, we have a different formula when we're looking at grouped data or data in a table. So x bar here is the sum of f of x divided by the sum of f, and that means that we need to calculate if this frequency is f, we need to calculate f times by x, so that 18 times by 5, and that gives us 90. 19 times by 7 gives us 133, and then we need to add these up. Remember, that's what the summation is telling us, so we add them all together, and this is what we would write at the end of this table here. So we need the summation of f of x and the sum of the frequencies as well, so that is 1108 and 54, and substituting these into the formula, we then have x bar is equal to 20.5, and so that's our mean. For the median, I'm going to use that same formula that we used on the last slide. So we've got n plus 1 divided by 2. There are 54 pieces of data we found out from the previous question on the mean, and so using this formula, the position of the median will be n plus 1 divided by 2, so the 27.5th piece of data. So if we work through this table, there are 5 pieces of data in that first category. There are 7 in the next category, so 5 add 7, that gives us 12 pieces of data. We then know there are 12 in the third category, so that's a total of 24 pieces of data so far, and that is then telling us that our 27.5th piece of data must be in the category there that's indicated. And so the median will be the x value within that group, which is 21. The mode is the most common. This is easy to pick from a table. It's just the largest frequency, and in this case the largest frequency is 18, and that refers to x being equal to 21. So the mode is 21. Now, as there is only one mode, we call this unimodal. So now we can work out the averages from a stem and leaf diagram as well. So starting with the mean, we need to add up all of the pieces of data. Now remember, if you're looking at a key, so the 3, the line, the 2, that makes 32. So in order for us to work out that this total on top is 315, then we need to add all of these pieces of data together. So 30 plus 32 plus 33 plus 20 plus 20, etc. And then we can count up. There are 15 pieces of data, so 1, 2, 3, 4, 5, all the way up to 15. So that gives us a mean there of 21. The median is found by crossing off the start and the end values, working our way through this table. So we start with the lowest and the highest and work our way to the centre. And so there is only one piece of data left there, so that is a median of 20. And then the final one, the mode, is the one that appears the most, and in this case this is also 20. So you need to be able to work out when it is good to use the mean, the median, the mode, and when it is not so good, and that depends on the data that you have. So there are some advantages and disadvantages for each of these averages when you calculate them. So looking at the mean, we have an advantage there that the mean will use every single piece of data in the sample or the population, and therefore it's representative. That's a key word of the data that you have. However, there is a negative, because it does take into account every single piece of data. It is affected by extreme values. Now you can see an example there. If most of your data is down at the bottom end, 3, 5, 5 and 7, but you then have a 63 as well, then the mean is skewed by that 63 piece of data, which can obviously affect the average value at the end. Looking at the median, we have an advantage there that it's not affected by extreme pieces of data, so this is like the opposite of what's true for the mean. However, disadvantage is that it only uses a couple of pieces of data, so it actually doesn't find patterns within the data. Now if you look at this in terms of the data here, we have 1, 3, 5, 65 and 67. And so we've got two extreme sets of data, and the median then wouldn't be representative of the data. And then the mode, an advantage here is it's the only average that can be used for what we call qualitative data, so things that are non-numerical. So if you asked people what were their favourite colour, then you could work out the mode for that data, so that's the only average that could be used. And a negative, a disadvantage, there could be more than one mode, or there may be no mode at all if every single piece of data is the same. So if we had say 1, 2, 3, 4 and 5 as our data, then there would be no mode at all. Now have a go at completing the exercises shown on this slide. So in today's lesson, I'm going to take a look at calculating the range and the interquartile range, and there's 3 different types of data that we're going to take a look at this for. This is the same data that we used when working out the averages. So if we take a look at the first set, so we're going to take a look at calculating the range and the interquartile range from a list of numbers. So for the range, we need to identify the largest and the smallest value and subtract them. And for the interquartile range, we need to put the pieces of data in order, work out the median mark, so that's the halfway point. We then work out the middle of the lower section, that's the lower quartile, which is found at the 25% mark, the quarter mark, and that is 19. And then we work out the 75% or 3/4 mark, which is the upper quartile there, and that is 21. So the interquartile range is the difference between these two values. So for a table of data, working out the range, we do exactly the same thing. So we're looking at the x values being the data points. So we've got 23 subtract 18, that's 5. The interquartile range, we would need to find the lower quartile position, which is n plus 1 divided by 4. There are 54 pieces of data, so 55 divided by 4 tells us we are looking for the 13.75 piece of data. So we do something very similar to what we did with the median. We accumulate all of the frequencies as we work up the table. So we have 5 pieces of data in that first category. We would have an extra 7, that makes 12 pieces of data in those first 2 categories, which means that the 13.75 piece of data will be somewhere in that section, and therefore the low quartile will be 20. We repeat the same process for the upper quartile using this formula, so 3/4 of n plus 1. That gives us 41.25. So if we continue counting on in the table, you can see that 41.25 will lie somewhere in this region, and therefore the upper quartile is 21, and the interquartile range is the difference between these two, therefore is 1. So looking at the stem and leaf diagram, With the range, we are finding the largest value and the smallest value, so we have 33 and 8, that is 25. And the interquartile range, so we need our lower quartile. Now we have to identify the median first of all, and then we do the same sort of process we did for working out the median, where we would cross backwards and forwards. So you do need to be mindful that if you're going to cross the diagram out to work out the median, you may struggle then to work out the lower quartile. So it might be worth doing this faintly in pencil rather than trying to sort of destroy the data underneath. So we are looking at these pieces of data. So these are all of the pieces of data that lie below the median, and we cross off just as we did before with the median itself to the highest and the lowest value until we get to the middle point. So this is 16 in this case. Repeating the same process for the upper quartile. So we have our data, largest and smallest value, working our way until we get our upper quartile there, which is 29. And so the interquartile range is 13. So we can construct a box plot or a box and whisker diagram using this information. So if we have our key pieces of data here, we need the smallest and the largest value, the upper lower quartile and the median mark. So working through nice and quickly, you can check this for yourself. So we'll identify each of those 5 key pieces of data. So here is a scale for our box plot appropriate to the data that we have. And we mark on straight lines for each of these key pieces of data. Median, we often use Q2, so quarter 2. Q3 is quarter 3, the upper quartile. Q1 is the lower. We create a box with these 3 pieces of data, and then we have what we call like the whiskers. So we have a straight line through the middle of that box up to the highest value, and we repeat the same process down towards the bottom end. One of the useful features of a box and whisker diagram is that it can easily identify outliers. Now there's a rule that is often used to work out outliers, and you just have that here in the centre. So we would say that a piece of data is an outlier if it lies 1.5 times the interquartile range above the upper quartile, or 1.5 times the interquartile range below the lower quartile. So let's work out what those boundary marks would be, and they are called upper and lower fences. So the interquartile range is 1.4, that's 8.2 subtract 6.8, and then we multiply that by 1.5, and that gives us our lower boundary mark there of 4.7. So any piece of data that lies below that would be classed as an outlier. And we can do the same on the other side. So if we have our upper quartile 8.2 and we add on the interquartile range to that, you can see that that lies at 10.3. So in this case we have some data that is an outlier on the lower side, so those values below 4.7 are outliers, but on the upper side all of our data does lie within that range up to 10.3. Now we need to identify these as well, and we do that. So if we take a look back at our data, we can then identify which piece of data are our outliers. So 4.1 is below the red dotted line, and therefore we mark this with a cross as an outlier, and we've rubbed out that lower whisker. We then need to use our next smallest value, the 5.7, as the lower bound for that bottom whisker. Looking at the top end, 9.9, the largest value is within the dotted line, and therefore we don't need to worry about having any outliers at the top end. If we are using a box and whisker diagram, we can also work out the skewness of a distribution by looking at the difference between the quartiles and having a look at the length. So we're actually comparing this length here, the difference between Q3 and Q2, and the difference between Q2 and Q1. So if we have the situation like this box plot down at the bottom, then we say that this is positively skewed because this length here is larger than the other side. And if we had a box where we had this situation, then we would say that that is negatively skewed. Now we can also produce a cumulative frequency graph and a corresponding box and whisker diagram to go with this. So using this information here, the first step is to work out the cumulative frequency, which means we are adding up all of the frequencies until we get to the very end. So the first category, we have 7 pieces of data. 7 plus 13 gives us 20, adding on 21, then 32, right up to the end. So we have 100 pieces of data. So here we have coordinate axes with an appropriate scale. And then we need to mark on these values. So the important thing with this is that we are marking on. So let me just get that first piece of data here. So the category 10 to 20, we mark 7 at the upper end of that box. So where we have 20, we go up 7. So that's that first piece of data. Now this cross before, because we have no piece of data before 10, we would mark 10 as 0. We continue to mark at the upper end of each of these boxes, intervals, and we should then draw ourselves a nice smooth curve through these points. So trying to work out the medians and quartiles then, so we're looking at the 50% mark, which just happens because we've got 100 pieces of data, that would be at 50, and then we can read off our value from the x-axis. And that gives us 43 in this case. The upper quartile will be at 75. That gives us a value of 51 on the x-axis, and then the lower quartile is approximately 33. So drawing the box and whisker diagram there. So we have our middle line for our median, upper quartile and lower quartile line to draw the box, and then the whiskers, the lowest point is 0. And the highest is at 70, and there's our box and whisker diagram. So here are the exercises for the work that goes alongside this PowerPoint. So the range and the interquartile range are measures of spread that do not consider all of the pieces of data, and therefore they may not be representative of the whole data set. And we have the variance and the standard deviation that do consider all of these pieces of data. So all of the pieces of data are taken into account when looking at these measures of spread, which can be more time consuming, but may be possibly more accurate as well. The variance will measure the amount that each single data point is away from the mean, so how far it deviates. And the standard deviation is equal to the square root of the variance. So we're going to have a look at how to calculate the standard deviation. Here is a set of data, and the first step is to calculate the mean. So the mean here is 7, this is x bar. Now in order for us to calculate the standard deviation, we're going to work out the difference between the mean and each of these data points. So the difference between 7 and 5, that would be -2. Between 7 and 6 is -1, and so on. From here we would work out the average distance from the mean. But the difficulty is now that if we add together all of these data points, it would come to 0. So instead of adding them together, because we have these negative values, we're going to square them first so all of those values are positive. So the variance is calculated using this formula. So it's the -2, the -1 in brackets, they are the differences between the mean and each single data point. We then square them, so we're removing those negative signs in front of the pieces of data. We are adding them together and dividing them by how many pieces of data there are. So this gives us 3.2. We can use this to work out the standard deviation by taking the square root. So the standard deviation here is 1.79. So this is telling us that each piece of data on average is 1.79 away from the mean. So there is a formula that we can use to work out the standard deviation as well. So this is one of the formulas that we use. So we have the summation, the sum of x minus x bar all squared divided by n. X, the first x inside of the bracket here, they are the data points. X bar is the mean. So that's what we did in that previous example. We take our data points, we work out the difference between the data point and the mean, we square them and then add them all together and divide them by how many pieces of data there are. Now if we were to expand this bracket, and you don't need to worry too much about this sort of idea, essentially this leads to a second equation. So the process here is less relevant than the fact that actually we can derive this second equation from the first. So there are two formulae that you need to be familiar with for the standard deviation, and these are just from that previous slide. So the square roots of, this is the first formula that we looked at with that very first example, where we looked at the differences between the means, squaring them and adding them and dividing by how many pieces of data there are. And this second formula was the one that was derived on the previous slide from that first equation. Now, it could be easier sometimes to use that second equation, but you do need to be familiar with both, and it depends on how a question is worded as to whether you would need one or the other, but you definitely need to be familiar with both of these. Now, they are given in the formula book, so do bear that in mind. And the other thing just to really focus on here is, if you're given a raw set of data, then what we mean by raw set of data is a list of data or a table of data, then you should be using your calculator to work out the values for the standard deviation and the variance. But some questions in an exam can give you certain things. So they might give you the sum of x squared as a value, or they might give you the sum of x minus x bar all squared as a value, which means you don't have the raw data and you would have to use the formula in these cases. Now, the last piece of information there, most of the data should lie within 2 standard deviations of the mean. So do bear that in mind when you're looking for outliers, and that's a different rule to what we looked at when we were looking at the box and whisker diagrams earlier. So here are 4 examples that you can use to work out the standard deviation, or an estimate for the standard deviation if you are looking at the group data in the bottom corner. Now, of these examples, the first, second and third one, there is a PowerPoint that you can use in order to determine how to use your calculator. So make sure that you have viewed that before continuing and checking your answers with these. Number 4 down at the bottom, this is an example where you do need to use the formulae that you are given for the standard deviation. So I shall take a look at question 4 separately. So answers to question 1, 2. Now this one's just working out the median values here, and there's the third standard deviation. So looking at example number 4. So here we're given the numerator of one of those equations, so that's 224, and we're told that we have 20 pieces of data. So if we substitute those into that first formula, that's 224 divided by 20. So that would give us our standard deviation for that first question. And then if we look at the second part of this question, so an extra 5 people were tested, and now we've got some what we call summary statistics rather than the raw data. We can substitute these into the second standard deviation equation. So we've got the sum of x, that's 162100. Now we need to divide that by n, the number of pieces of data. So we've got 20 from the start plus 5, so that gives us 25. We then need to subtract the mean squared, so that's x bar squared. Now we're given the sum of x, so if we want to work out the mean, then we need to divide 2011 by 25, and then we need to square this, so this is x bar squared, and then we need to take the square root of all of that, and that gives us 3.66. Now you can take a look at exercise 4.4 on page 157.